Hello learner, welcome to today's session, and today we're going to talk about electronic configuration, and our subtopic today we're going to talk about orbitals, and later on we're going to cover about the energy levels. We're going to cover the quantum numbers and what they represent in as much as electronic configuration is concerned. So we are going to have a clear introduction of the four quantum numbers, and then we are going to define what each of the quantum numbers is going to address as much as the electrons our electron addresses are concerned. So let's talk about orbitals. For us to have a better understanding of the where these electrons live, we must have a better understanding of an orbital. So what is an atomic orbital? An atomic orbital is a region or space where an electron is most likely to be found, and it's not a fixed part. You can think of it as the probability cloud, which is just like an orbit or a planetary kind of a thing that defines the path taken by what? The path taken by the electrons as they revolve around the nucleus. Remember the Bohr model that we covered earlier on. The Bohr has described that electrons they occupy energy levels, whereby the first energy level, the first one, second one, third, up until infinity. So it's this scientist by the name Bohr had described that atoms are quantized, and they increase in energy as you progress away from the nucleus. Remember an atom, maybe I can draw a simple structure of an atom. Assume that this dot at the center is the nucleus. So you have the first energy level, and then you move to the second energy level, and then you move to the third energy level, and then you move to the fourth energy level, up until infinity. That's what Bohr had described, and he defined a rule that the far you get away from the nucleus, the higher the energy increases, and the closer you are to the nucleus, the more energy is. So the lower the lower the energy, the closer you are to the energy, to the nucleus. Maybe if we can move on to our next slide, and we're going to cover the quantum numbers, and we are going to start with the first quantum number. The first quantum number is what we call the principal quantum number. This is what we call the principal quantum number, and this principal quantum number is designated as n, and it describes the energy level or the size of an atom, not the size of an atom, sorry, the size of an orbital. It describes the size. So n describes the size, of an orbital, and as n increases, the electron is far from the nucleus. This one, I just spoke about it earlier on. So, and it's always a positive number. It's an integer, and it runs from 1 to infinity. That's what we call the energy level. So as you can visualize from this, assume this is the center, the nucleus. So this is an electron that revolves around a nucleus. So the more you increase the energy level, the farther you get from the center, and this is what the principal quantum number n tries to describe. Moving on, we can also look at the next quantum number, and the next quantum number is what we call the angular momentum. The angular momentum is designated as an L. Some books they denote it as an M. No, the most it's usually denoted as an L. It's denoted as an L, and its purpose, it describes the shape. It describes the shape of an orbital. I don't know if you can see. Maybe let me just zoom this a little bit. Yeah, I think that one is much better. So it describes the shape of it describes the shape of an orbital, and we are this one is very important because it's the one that we use to define the orbitals. We have for the most common orbitals, we have the s orbitals, we have the p orbitals, we have the d orbitals, and we have the f orbitals. These are the most common orbitals that we have. And the angular momentum, some books call this as quantum number. This is the quantum number that defines the shape. So for example, an s orbital is spherical in shape, a p orbital is dumbbell shape, a d orbital is usually a clove shape like this. These are a d orbital, and then you have an f orbital, which is a very complex, a multi-lobed shape. And if I can just draw, it's something that looks like this. So it's more complex in nature because of the higher energy levels that exist when you go further away from the nucleus, meaning the randomness of that electron increases, and this is what the angular momentum tries to explain. So as we have said, it's an s orbital is usually spherical in shape, and the first orbital per sublevel. It has only one orbital per sublevel. So in orbitals we have sublevels. So the first orbital has only one sublevel, and the number of sublevels will always be equal to the number of the energy level at which uh, sublevel or that electron dwells. So the p orbital, it's dumbbell shaped, and it has three orbitals dwelling in it, and these three orbitals we're going to allude to them later on in our course. um, it's kind of the orientation of each of the sub levels uh, in relation to the Cartesian plane. So for example, we say the p orbitals, they are dumbbell shaped, a dumbbell like this. This is a dumbbell, so they're dumbbell shaped. So you can get, for example, a py orbital subshell which aligns in the x-axis, that is the px. This is a px orbital. We have a py orbital. A py orbital will align itself on the y-axis of the Cartesian plane, assuming this is our Cartesian plane, like this. This is the x, and then this is the y, and this is the z, this is the y. So a py will lie like this, and then we have a z orbital which will lie on the z-axis, like this. So we have a z. So all this is what the angular momentum tries to explain. It gives us the subshell levels and the number of subshells within that orbital. So we have the d orbitals, and they are clove shaped, just like this clove that I've drawn. The clove leaf shaped, and it usually dwells with 5 orbitals. We're going to visualize this later on. I'm going to send you a link on a video that speaks more about the orbitals and the subshells within them. and you are going to get a better understanding and a clear visualization of of the orbitals, of this concept of orbitals. And then lastly, we have the p orbitals, I mean the f orbitals and the f orbitals. They're more complex and they are multi-lobed shape, so they have several lobes between each node of the orbital. So moving next to our next quantum number, we can talk about the last quantum number, which is the okay. Before we talk about our last quantum number, which is a magnetic spin, maybe you can talk about the relationship between the n and the l. That is the principal quantum number, and we're going to talk about the relationship between the principal quantum number and the angular momentum. So when our principal quantum number is 1, that is, we are at the first energy level. It means that we have how many suborbitals? We have only one suborbital which exists within that level, and that suborbital is only a 1s subshell, and this means that our L will be less than the principal quantum number 1, which is 0, meaning when n is equals to 1, our principal quantum number is 1, we have 0 subshell levels. That's why we have these three, they are empty. So when we move higher to the higher energy level, for example, we are at energy level number 2. At energy level number 2, our principal quantum number will be equal to n minus 1, which is 2 minus 1, which is what? 1, meaning we'll only have one subshell level, and this subshell is a what? It's an s orbital, which is spherical in shape, and this subshell is a 2s, and a 2p. We are going to have two subshell levels, meaning we have two subshells within the energy level number 2. That is a 2s orbital and a 2p. Why do they exist? Because the possible combinations that we can get is either a 0 or a 1 within that the principal quantum number when it is equal to 2. So when we increase to our principal quantum number to be 3, we are going to get 1, 2, 3, 3 subshells. That is a 3s, we are going to get a 3p, and we are going to get a 3d. And then the third one, or the third option, exits, meaning it's going to be empty. So, and the process goes on and the series continues on. For example, when we are at the subshell number, at the principal quantum number 4, we have the 4s, we have the 4p, we have the 4d, and the 4f subshells. This is the most possible combination. This is the possible combination that we can get. So the key pattern is that the value of n equals to the number of subshells. For example, if you have n principal quantum number, for example, you have at the nth, that is the fourth subshell, the fourth energy level, we're going to get exactly 4 subshell levels, which are the s, p, d, and f, meaning all the orbitals are at the principal quantum number 4. We are not going to talk about energy level number 5 because most of the periodic elements do not exist, although there are some that have electrons at their fifth energy level, but we are not going to talk about them because they are not part of they are beyond the scope of this tutorial. Moving on, let's talk about the magnetic spin. Let's talk about the magnetic spin. The magnetic spin. This is another principle. I mean, this is another quantum number, and we call it quantum number 3, and it's designated as ML. It's designated as ML. This one, its role is to describe the orientation of an orbital in the space. Remember, we talked about the SPD and F orbitals, right? For example, we can have a px orbital, we can have a py orbital, we can have a pz orbital. So what is the role of the magnetic quantum number? The magnetic quantum number, it helps us to know each orientation of an orbital within what? The orbital in space. And its value ranges from what? From -1 to a +1, meaning the magnetic quantum number, for example, you're at a subshell level that is L is equals to 0, meaning we will have one orbital. When the subshell level L is equals to 1, our ML values will range from -1 to +1, and 0 is included as well. 0 means we are going to have an s orbital within this angular momentum when it's 1. For example, a good example is this one that was spoken about. We are going to have a px, a py, and a pz orbital when the principal quantum number is 1, and I mean when the principal quantum number is 2 and our angular momentum is going to be 1. So we are going to have the px, py, and the pz subshells. So, and the role of the magnetic spin is going to give us the orientation. So we're going to get a py, for example, if this is the Cartesian plane like this, and then this is a z, and then this is a y, and then this is an x. So the px, the p orbitals, we say they are dumbbell shaped. They're going to lie at this, like this. And the pz, if I draw the Cartesian plane as well, the pz, they're going to lie on the z axis of the Cartesian plane like this. So this is the z, and then this is the y, and the py, they're going to lie on the y axis. So assume we have the y axis like this. This is the y axis. So our py is going to lie on the y axis like this, and this is the z, and this is the y, the x axis. So that's the role of magnetic spin. It's going to give us the orientation, of that orbital within the subshell of an atom. So moving on, we're going to talk about our last quantum number, and the last quantum number is the magnetic spin. The magnetic spin. The magnetic spin. Remember, the magnetic spin is what defines how electrons aligned within a same orbital. Remember, electrons do not exist in isolation in most cases because they yearn for stability, and therefore they tend to pair. So a magnetic spin could be very important in giving us toward orientation. For example, we have one pair facing up and then another pair facing down. So meaning a magnetic spin is it's in every electron has an intrinsic spin, and only two possible values exist, and that's a positive, meaning one of these is a positive value, and when it faces down is a negative value. So we cannot tell which is a positive one, which is a negative one. But the role of the magnetic spin, which is designated as an ms, sub s, is what we call a magnetic spin, and it's going to give us what we either it's an up spin or it's a down spin. So that's the role, and that's this going to help us have all the all the all the requisite addresses that define an electron. So I think so far we've covered much about the electron addresses, and maybe for us to have a clear understanding, we're going to talk about all the four quantum numbers and how they relate to what we call the Pauli principle. The Pauli principle, this is what will help us define that will help us get the comprehensive location of that electron. So electrons, they are usually defined by the four quantum numbers, just like we spoke earlier. The principal quantum numbers, which determines the energy level. So it defines whether it's the first energy level, at the second energy level, or at the third energy level. And then we have the angular momentum that defines the shape. Either it's a spherical shape, that's an s orbital, it's a p orbital, or it's a clove shape like the d orbitals, and this is an f orbital. So it's going to give us the shape. And then we have the magnetic spin. The magnetic spin will give us the orientation, whether it's facing up or it's going to face down. So that's what the magnetic spin will help us do with it. And finally, we're going to talk about the angular momentum. I mean, the magnetic number. The magnetic number is going to give us the orientation on the space or on the Cartesian plane of that particular orbital. Right. So for that being said, maybe we can move on to our second last slide, and in this one I'm going to give an example of how we can fully define an electron when writing an electronic configuration. For example, you have an electronic configuration of an electronic configuration of an electronic configuration of 2p5. So what does it mean? The sub level is what? Is p. This p will give us the sub level, and then it means when the sub level is 2, it means the principal quantum number, this is n, this is going to give us n, and then this one is going to give us l, that is the sub level, and then this one is going to give us the number of electrons, which are what? Which are 5. And the 5, they either, for example, you have 1 2 3 4 5 electrons there, so they can either be like this, an upward speed, or all of them, or they can pair up. For example, they can pair 1 2 3 4 and 5. They can pair 1 2 3 4, and then the fifth one, which is unpaired. So we don't know the possible combination, but we're going to talk about it later on when we are going to apply the Pauli principle and the Hans later on the stages. So this is what is going to give us a complete address of an electron. So the 2p speaks about the principal quantum number. And then the p is going to give us the angular momentum, and we're going to get our magnetic spin in the five electrons. They can either be paired or unpaired, or they can have two pairs and a single electron. All right, so I believe we've come at the end of our session, and lastly, I'm not going to talk about this. Maybe I can leave you this one as an assignment. You go and look at it, and you apply the same 4 steps of giving the N, the L, the ML, and the MS. So thank you very much. That's our session today, and I believe later on we're going to speak more about writing electronic configuration. Bye for now.